Friends, welcome back to sakalvidya.com and myself Shivaramakrishna Sharma. In today's session, we are going to have a discussion on 13th chapter, that is thermodynamics, from our junior intermediate physics. So this 13th chapter, that is thermodynamics, which has a weightage of 8 marks. So we are going to expect one long answer type question from this thermodynamics. The first question from our thermodynamics, that is, explain the reversible and irreversible process and describe the working of Carnot's engine and obtain an expression for the efficiency. In chemistry, we have seen there are two types of reactions. One is reversible reaction and irreversible reaction. In a similar manner, here we are going to discuss about reversible and irreversible processes. So let us have a discussion on what is reversible process. So reversible process. So what is reversible process? In order to understand the concept of this reversible process, let us take a small example from our daily to day life. For example, we are having ice, which is in the form of a solid state. Keep it aside in a room temperature for some period of time. So what happens there? From solid state, the ice starts melting to liquid state, means it forms from solid state to liquid state. So the ice transfers into a liquid form. Again, transfer this ice into your fridge. So what happens? It starts freezing, which means again it attains its original shape from liquid state to solid state, which means the ice starts freezing from water form to ice form, which means this process that can be retraced back to its original process or original shape. This is a best example for your reversible process. So the best example for your reversible process is melting up of ice. So the process that can be retraced back in its opposite direction, the system passes through the same state as in the direct process. Finally, the system and surroundings return to their original state. So this state of process is called as reversible process. So the best example for your reversible process is melting up of ice, vaporization of water. So from ice to liquid, from liquid to again your ice. So this is the best example for your reversible process, so which can retrace back to its opposite direction. Retrace means which we can bring back. So this is called as reversible process. So what is irreversible process? So that process which cannot be retraced back in its opposite direction. So such type of process is called as irreversible process. So irreversible process, the process that cannot be retraced back in the opposite direction, is called as irreversible process. So what are the examples for your irreversible process? Examples are as follows: work done against the friction, and free expansion of the gases. So these are the two examples for your irreversible process. So those processes which cannot be retraced back in its opposite direction, so such type of process are called as irreversible process. So Carnot's engine. So actually Carnot's engine was developed by Nicholas Carnot, who was considered as the father of this thermodynamics. Nicholas Carnot was a French scientist or a physicist who discovered this Carnot's engine. He is also called as father of thermodynamics. So what is Carnot's engine? A reversible heat engine operating between two different temperatures is called as Carnot engine. For example, here we are having a working body. So which is working between two different temperatures. So which means, for example, here having a source of hot temperature, that is TH. Here we are having a source of cold temperature. So which is working under two different temperatures. So this is a QH and Q sub X. This double is the work done by the body. So this is a Carnot engine, which is a reversible heat engine operating between two different temperatures, is called as Carnot engine. So this Carnot engine consists of source at high temperature, a working substance as I told you, insulating stand, and the last one is sink at the lower temperature. So this Carnot engine undergoes the following process: A. Isothermal expansion, B. Adiabatic expansion, C. Isothermal compression, and D. Adiabatic compression. So what is this isothermal and adiabatic? Let us have a discussion on what is isothermal and adiabatic process. Let us understand the concept of what is isothermal and adiabatic process. So what is isothermal process? The process in which the temperature remains constant. So which means delta T is equal to 0. So the process in which the temperature remains constant is called as isothermal process. So whereas adiabatic process, the process in which it occurs without the transfer of heat between the thermodynamic system and its surrounding is called adiabatic process. So what is adiabatic process? The process in which it occurs without transfer of heat between the thermodynamic system and surrounding is called adiabatic process. So we know that in Carnot engine these four types of processes are done. One is isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. So in order to understand this concept, we must plot a graph between pressure and volume. So as shown here. So we must plot a graph pressure versus velocity. So velocity on x-axis and pressure on y-axis. So here we are going to get three terms. One is pressure, volume, and temperature. So based upon this graph or based upon this diagram, we are going to understand the concepts of what is isothermal expansion, adiabatic expansion, and isothermal compression and adiabatic compression. Let us have a discussion on what is isothermal expansion. So what is isothermal expansion? So if you see here, A is known as isothermal expansion, where it changes from P1 V1 T1 to P2 V2 T1, where P is pressure, V is volume, and T is temperature. So in this expansion of gases takes place its state from, as I told you in previous case, P1 V1 T1 to P2 V2 T1, where P is the pressure, V is velocity, and T is temperature. Heat Q1 is absorbed by the gas from the reservoir at the temperature of T1 is equal to the work done by the gas on the environment. So which means here work done is equal to heat absorbed. Which means W1 is equal to Q1. We know that W1 is equal to Q1 is equal to N into R into temperature 1 times of log to the base E V2 by V1. Let us assume as equation 1. So by using the condition work done is equal to heat absorbed, that is W1 is equal to Q1, where Q1 is the heat absorbed and W1 is the work done, we know that N into R into T1 log E to the V2 by V1. So this is the isothermal expansion. Let us assume as equation 1. So adiabatic expansion, if you see here from this point to this point, it changes from P2 V2 T1 to P3 V3 T2. So this region is called as adiabatic expansion. So what is adiabatic expansion? The expansion of gases takes from P2 V2 T1 to P3 V3 T2, where P is the pressure, V is velocity, and T is temperature. Here W2 is the work done by the gas. So in adiabatic expansion we have W2 is equal to NR times of T2 minus T1 by gamma minus 1. This is a work done formula for adiabatic expansion. Let us assume as equation 2. So what is adiabatic expansion? The expansion of gases takes place from P2 V2 T1 to P3 V3 T2 as shown in that figure. As shown in the adjacent figure, this is called as adiabatic expansion. In the case of expansion, we have seen heat is absorbed, whereas in the case of compression, heat is released. So when heat is released, that condition is called compression. So what is isothermal compression? The compression of gas from P3 V3 T2 to P4 V4 T2, which means from this region to this region is indicated as C. This region is known as isothermal compression, which means the heat Q2 released by the gas on the reservoir at the temperature of T2 is equal to the work done on the gas by the environment. In previous case, heat is absorbed, whereas in the compression, in this case, heat is released. So work done is equal to heat release, which means W2 is equal to Q2. So W2 is equal to Q2 is equal to nRT2, temperature 2, log base C to the power of V3 by V4, velocity 3 by velocity 4. So let us assume as equation 3. So in this case, heat is released. So this condition is isothermal compression. Adiabatic compression. So what is adiabatic compression? The compression of gas takes place from P4 V4 T2 to P1 V1 T1. So from this region to this region is indicated with D, which means that is called as adiabatic compression. So A to B, from that region heat is absorbed, whereas from C to D what happens? Energy is released. So from C to D, this region is called compression region, whereas from A to B, that region is called expansion region. So let us derive formula for adiabatic compression. So work done V4 is equal to nRT, let me write the formula. W4 is equal to N into R times of T1 minus T2 by gamma minus 1. So let us assume as equation 4. The total work done by the gas in one cycle be W suffix T, which means W suffix T is equal to W1 plus W2 minus W3 plus W4. Is it clear? So what is W1? From our basic equation we have N into R T1 log V2 by V1 plus what is W2? NR T1 minus T2 by gamma minus 1 minus what is W3 here? NR T2 log V3 by V4 plus what is W4? NR T1 minus T2 by gamma minus 1. So let us subtract. So NR T1 log V2 minus V1, V2 by V1 plus NR T1 minus T2 by gamma minus 1 minus of NR T2 log V3 by V4 minus of NR T1 minus T2 by gamma minus 1. So what do you observe here? Plus NR times of T1 minus T2 by gamma minus 1 and minus NR times of T1 minus T2 by gamma minus 1 gets cancelled. So this and this gets cancelled. So what is left here? nR T1 log V2 by V1 minus nR T2 log V3 by V4. So what is common here? From this equation and this equation, nR is common. If you take nR is common, n into R times of T1 log V2 by V1 minus T2 by log V3 by V4. Let us assume as equation 5. Let us assume as equation 5. Now let us find the efficiency of Carnot's engine, which means efficiency is equal to Q1 minus Q2 by Q1. Is it clear? So can we write like this? 1 minus Q2 by Q1. So if we multiply Q1 with 1, again we are going to get this above equation itself. So if you multiply Q1 with 1, we are going to get again the above equation itself, that is Q1 minus Q2 by Q1. So as we know, Q2 is equal to nR T2 log V3 by V4 and Q1 is equal to nR T1 log V2 by V1. So let us substitute these two equations Q2 and Q1 in the above equation, in this equation. So we are going to get the efficiency. So as we know, efficiency is equal to 1 minus, what is Q2? nR T2 log V3 by V4 divided by nR T1 log V2 by V1, which means 1 minus nR by nR into T2 by T1 into log V3 by V4 by log V2 by V1. Here nR get cancelled. So what is left here? 1 minus T2 by T1 into log V3 by V4 by log V2 by V1. So let us assume as equation 6. So this is the efficiency of the Carnot's engine. So in adiabatic process we have T1 is multiplied with V2 whole power gamma minus 1 is equal to T2 into V3 whole power gamma minus 1. Let us assume as equation 1, whereas T1 into V1 power of gamma minus 1 is equal to T2 into V4 whole to the power of gamma minus 1. Let us assume as equation 2. So from equation 1 divided by equation 2, equation 1 divided by equation 2, which means T1 V2 whole power gamma minus 1 by T1 V1 whole power gamma minus 1 is equal to T2 V3 whole power gamma minus 1 by T2 V4 gamma minus 1. So what do you observe here? In the left hand side, what do you observe? So T1 gets cancelled, whereas in the right hand side T2 gets cancelled. What is left here? V2 whole power gamma minus 1 by V1 whole power gamma minus 1 is equal to V3 whole power gamma minus 1 by V4 whole power gamma minus 1. So it is in the form of A power m by B power m, which means A by B whole power of m. Is it clear? Similarly, we can write V2 by V1 whole power of gamma minus 1 is equal to V3 by V4 whole to the power of gamma minus 1. Similarly, we are going to get V2 by V1 is equal to V3 by V4 when gamma minus 1 is constant. So let us assume as equation 7.